All right, welcome back, you guys. Good morning. Let's talk about, let's pick up where we left off yesterday. Linear momentum is always conserved, but what about energy?
Energy, what is that stuff? Man, that's a hard one to. How many kinds of energy are there?
Well, there's quite a few kinds of energy. We've got the thermal energy, nuclear energy, mechanical energy, kinetic, we got all sorts of different things, right?
Yeah.
So ultimately, total energy is always conserved. Mechanical energy.
Mechanical energy. Well, that's the one where we ignored a bunch of other energies just to make it simpler. What were the energies that we considered?
We're considering kinetic energy and potential energy.
That's right.
With mechanical. So since motion is involved, kinetic energy is the mechanical energy of interest. This is what we care the most about, and this is what we're going to focus on. If kinetic energy is the same before and after the collision, we have elastic collision.
An elastic collision.
And
here's an example.
A 2 kilogram ball rolling at 4 meters per second strikes a stationary 2 kilogram ball. The original ball is stopped. How fast does the second ball roll away?
We need that pyramid thing.
We need the pyramid. Oh, we were going to do this earlier in the previous video, but that's okay. Well, what do we know about the conservation of momentum?
Before is equal to momentum afterwards.
Yes. And so we're going to go.
You got two things here, 1 and 2.
Okay. And then.
Well,
the equation.
before I go on any farther here.
Great. Yeah. Okay. So the beautiful thing about setting it up like this is that we can get rid of some stuff, right?
Yeah.
Okay. So we've got a 2 kilogram ball. Rolling at 4 meters per second, we'll call that.
So that's the first one. It has momentum. The other one is stationary. What does that mean?
Well, it doesn't have momentum, so I'm
Means
just
it's
going to
not
go ahead
moving.
and get rid of that one.
All right.
And then it strikes a stationary ball 2 kilograms away. The original ball is stopped.
Okay, so that means that after the collision, the original one has no momentum, and we want to know how fast does the second ball roll away.
Okay, so now we can actually plug in our equations, right?
Yep.
And I know mass volume equals.
Velocity.
Sorry.
That's okay.
It's been one of those days.
We're talking about density here, right?
Yeah. D equals m divided by v.
That's right.
Okay. And then mass 2 and velocity 2 prime. Okay. Let's get our numbers here.
And what do we want to solve for?
We want to solve for how fast the second ball is rolling away.
So before you put the numbers in, solve for the thing you're looking for.
Great idea. Let's do it. How do we get this by itself?
Yeah.
Okay, so V2 M1 V1 over M2 prime. Let's go ahead and plug those numbers in here, yeah?
Okay.
The mass of my first ball is?
2 kilograms.
My velocity is?
4 meters per second.
Okay, and I'm dividing that by, what's the mass of my second ball?
2 kilograms.
2 kilograms, okay, so 8 divided by 2. Mr. Boykin, this is easy.
It is easy.
And what do we notice about the answer?
It's
the same as
the same. Yeah, that's an elastic collision.
Yeah.
Because if we calculated the kinetic energy, it would come out the same.
Okay. So that was an example of an elastic collision. Here's an inelastic collision. If kinetic energy is lost to other forms of energy, we have an inelastic collision.
Yep.
Again, linear momentum is always conserved.
So you might have, when the collision happens, a loud noise.
Bye.
You might have heat. There are any number of things that might steal kinetic energy into other forms.
Mm-hmm. But it is always conserved.
But the
it's
momentum is always conserved.
Would you say stolen into other forms? I like
Yeah.
that. Okay, so let's do our lab. You ready?
Let's do it.
Let's do it. Okay, so I want you guys to get a good look at this data table And Boykin is gonna hold his hand nice and steady. Pause the video, copy this amazing chart down in your notes. I will also probably upload it into.
Yeah, it would be better if they could just have this where they could fill it in.
So as we go through this, I am not going to write down the numbers. You guys are responsible for the numbers. So
We'll just call them out.
yeah, we're just gonna call them out.
So what's our setup here? It looks like we have 2 carts on the track.
Yeah, pass car 1 and pass car 2, red and
We
blue.
have 2 photo gates that will tell how much time that big long thing is in, and then the LabQuest will calculate this velocity.
And the first thing we want to do is write down for our trial 1 is the mass of our cart.
So each mass is 0.250 kilograms.
So they would write 0.250 kilograms right here,
Trial
right?
1 for cart 1 and for cart 2.
And for cart 2, here and here. Okay. Let's go ahead and I'm gonna push play.
Okay, now hold on a second. What's this one has a plunger that will make it go down the track, so it'll have momentum. How much momentum? What's the velocity of this one right now?
0.
It's not moving. It's 0. So cart 2 before velocity is 0.
Y'all can see that?
All right.
Okay, here we go.
All right. So start them up.
Oh yeah, I almost forgot. Dwing. And
Okay, stop them. I noticed that first cart stopped, just like that problem we did a minute ago.
look at this.
So the velocity of number 1 before 0.763, and then afterwards it came to a stop.
Oh yeah, right, exactly right there. We didn't touch it, and so that means that after right here, for velocity, we're gonna write that 0.76. Oh no, this is for after, right?
No, the cart 1.
Oh,
came to a
you're
stop.
right, 0 right here.
So before the collision,
It's gonna
is
be
0.763.
yeah.
Okay, now cart 2 was 0 before. Now it is
0.723.
Oh,
That's
little
dang
frictional
close.
losses there. Okay.
Yeah.
All right, so you can calculate the momentum and the kinetic energy later. Let's get some more data.
Okay, let's push these guys back.
Let's see, what should we do? Put it in the blue one. Okay, the mass of the red one is still 0.250. The mass of the second one is now 0.500. Something's going to be different.
Okay,
So this is trial 2.
trial 2.
Okay, stop them. That's okay. Stop them. I noticed that the red one had a velocity positive before the collision and then a velocity negative after the collision.
So,
So
for
this
our
is
trial 2,
trial 2.
for our first cart, our initial velocity, our velocity right here is going to be,
0.781.
and then our mass, so for cart 2, it was 0.5 right here,
Yeah.
and our velocity in the beginning was 0, right?
0.
Okay, and our velocity in the end is going to be 0.484 meters per second.
0.484. Now,
Yeah.
this,
Oh yeah, let's show them the second
and
one.
then now this is going to be negative 0.172. So cart 1
And where is
after.
this? Yeah, where's this from? So it went like it hit the guy right here, right?
Yes.
And it went this way, and then it went back because
This guy went back slowly.
right there.
And
yeah.
so that momentum afterward, the velocity afterward should be negative 0.172 meters per second. Got it?
Sweet.
Sweet.
Okay. What should we do next?
Well, let's put the mass on the red cart. All right.
Okay. So I'm gonna go ahead and start these, and here we go. Oh no, we want to do that one again.
Yeah, we got to
I
do
couldn't
that
remember.
again because the red one had momentum
You're
after
right.
the
I should have
collision.
touched it. We want to
That's
calculate
all
the
right.
momentum.
No harm, no foul.
Let me pause that, and we're gonna start again. 3, 2, 1. And
Could get that out of the way, and it's gonna slowly, dog lips. We're gonna have to do that again. That won't count. I've got an idea. Let's just move this
A little bit further.
that way a little bit.
All right. Here we go.
All right, third time's the charm. This is trial 3.
That's how we have trials. This is trial 3, yes. Okay, here we go.
Go, 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 go. Okay. Now you can see it was losing. It was losing some speed there.
Okay, trial 3, mass of the first cart is now 0.5.
Yes.
Mass over here is 0.25. In the very beginning, our velocity was 0.541 meters per second.
0.541 meters per second. Okay.
Okay, and then for our cart 2, the velocity in the beginning, it wasn't moving, right?
It was 0.
It was 0. And then our velocity after was
0.691. But now we need the velocity of the red card afterwards,
yeah.
so you got to move the data thing over.
doink 0.092. So that's
So
gonna
cart
go
1 after.
right there.
Cart 1 after. What was it? Point 0?
0.092.
All right. And that was trial 3. That's 3 trials.
Okay, so now what do they need to do?
Well, let's get some data for, what we'll do is we'll get the data for both elastic and inelastic.
Okay, so for our inelastic,
Before we're going to turn these around, and there's Velcro. An inelastic collision, they're going to stick together. And what we're not going to use the,
is it all the way in there? Oh, there we go.
my bad. So you're just, all you got to do is give it a shove.
Okay, so masses are both 0.25.
Yep.
Velocities, let's go ahead and do it. And here we go, we start. I'm just gonna go ahead.
Just give it a shove.
Give it a shove.
Got to give it a bigger
I need a
shove.
bigger shove.
Well,
Bigger shove!
Yeah.
Pause. And it is like, well.
and you can see they're both going to have the same velocity afterwards because they're stuck together. Yeah, give it a bigger shove than that. Not too big.
Ready, and go. Oh wait, I didn't push play. Yeah. This is really a 2-person lab if you guys hadn't figured that
It
out.
is. It is. You need 2 people doing this.
And play. And here we go. There we go.
All right. So the mass before, and I realize now, and what we're going to do instead of cart 1 and cart 2, the mass before was
0.25.
0.250, and the mass afterwards is
0.5.
0.5.
Yeah. And our velocity before for cart 1 is going to be 0.600 meters per second.
And then
And
cart
then-
1 and 2 stuck together.
Yeah,
is
okay, so it's going to be 0.256.
0.256.
So this over here should really be cart 1 plus cart 2, right?
Yeah, they're stuck together.
Plus 1 like that. Whoops. Okay. All right, so let's add some, should we add some mass?
Let's do it. Where do you want to put it?
Yeah. Let's put it here first.
Here?
Yeah. So I'm really gonna have to make sure I.
Yeah, you're gonna have to.
Right?
You're gonna have to whoop that sucker.
And here we go. Oh. And. There we go. And pause. Pause.
So before the mass of cart 1 was 0.250, and afterwards, now it's
0.750.
0.750 is the total mass.
So 0.750, 0.250, and then our cart in the very beginning, the velocity is going to be 0.684,
Yes.
and then
both of them
velocity after
afterwards.
0.2.
Oh, oh.
Oh, and that's going to go right over here. Okay.
Now let's put it in the red
Switch
card.
them. Okay. And here we go. Play.
Ooh, I like that.
Doink, doink.
It's a good one. So mass
Oh, shoot.
before was 0.50.
This one didn't go.
Go!
That was right. These things happen. Come on, nails.
Nails don't fail me now.
There we go. All right, here.
Yeah, you should get the little wheels going around
Yeah, the
in both
wheels.
of them.
There we go. There we go. 1, 2, 3. And pause. Okay, we're done. So mass of cart 1 is going to be 0.5.
0.5.
Together again, 0.75.
Yep.
The velocity of my red cart, cart 1 in the beginning, is 0.628.
Yes, so that's a velocity of cart 1 before.
And then cart 1 and 2, it's going to be 0.384.
Yeah, so it's instead of before and after, this is going to be before and this will be after.
Yeah, so I can cross this one out, right, Boykin?
Yep.
Like this, and then I can cross the before over here off, right?
Yep.
Like this, ladies and gents.
Yep.
Okay, so if you're feeling nervous about what we're telling you to do, now you know.
All right,
Okay.
now they need to calculate all the momentums using the mass and the velocity. They need to calculate all the kinetic energies, mass and velocity.
That sounds like a lot of fun.
Yeah.
Okay.
So, what are the questions? I know there's some questions.
Oh, they're right here. It says, what was the total, it says, that's,
I think what we need to do is the law of conservation of momentum holds in each collision, and understand that there is some error. Just because it's electronic doesn't mean it's perfect.
so this question, Boykin says, does this result support the law of conservation of momentum?
I like that.
Yeah. And then calculate what is the total momentum, what's the kinetic energy, and then does this result support the law of conservation of mechanical energy?
Okay, so there's two good. I like those questions. So for each trial, does it support the law of conservation of momentum, and does it support the law of conservation of mechanical energy? That should keep them busy.
That's good. Go ahead and begin.